So today we're going to take a look at sections 11.3 and a little bit of 11.4, looking at the cross product of two vectors. Our learning target for today that we can find the cross product of two vectors, we can find a unit vector that is orthogonal to two vectors, we can find equations for planes in space. So the cross product of two vectors, go back a second. Let me remind you. So like two-dimensional vectors, three-dimensional vectors can also be represented in multiple ways. The primary ways that you're going to see is component form with the angle brackets. Vector v is equal to angle bracket v sub 1, comma v sub 2, comma v sub 3, where those are your x, y, and z components. Or we can use kind of that linear combination form, the standard unit vector notation, where v is equal to v sub 1i plus v sub 2j plus v sub 3k. So if we have a vector u and a vector v in either the unit vector notation or component form, okay, the cross product of vectors u and v is the vector u cross v is equal to u sub 2 times v sub 3 minus u sub 3 times v sub 2i minus u sub 1 times v sub 3 minus u sub 3 times v sub 1j plus u sub 1 times v sub 2 minus u sub 2 times v sub 1k. Or you can have the same thing but written in component form. Notice that for your x component and your y component, those are positive. Well, not necessarily positive, but the y component is the opposite, right? This way, this negative sign, this minus sign in front of what you get from those this step here. Okay. Now, before you go trying to memorize this formula, let's take a look at kind of where it comes from. It relates a little bit back to determinants of a matrix. So if we take the x, y, and z components of our two vectors, and we just wrote I, J, and K above them, okay? To get the number that's going to go in front of the I, or to get your x component, we're going to ignore the x component column and then find the determinant of the numbers in the two remaining columns. And you might recall to find the determinant, you find the product of the first diagonal, subtract the product of the second diagonal. So that's where this u sub 2 times v sub 3 minus u sub 3 times v sub 2 comes from. To get our y component, we're going to ignore the terms in the y column, and then we're going to find the determinant of the remaining two columns. So if we multiply our first diagonal, u sub 1 times v sub 3 minus u sub 3 times v sub 1. And then we have to remember just to make that term opposite. And then to get our z component, we're going to ignore the numbers in our z column, and we're going to multiply our first diagonal, u sub 1 times v sub 2 minus product of our second diagonal, u sub 2 times v sub 1. So that's where those products are coming from. The cross product gives a vector that is orthogonal or perpendicular to both of the original vectors. So let's take a look at example 1. We're going to find the cross product of vectors a and b and show that the cross product of a and b is orthogonal to both a and b, where vector a has components of 2, 1, 3, and vector b has components of 1, 3, 2. Just reminding you of our formula here. So now if we put in our x, y, and z components for vector a in this row, and then for vector b in the second row, then we can substitute those values into our formula, or again, you can think about it in that determinant way. So for our x component, we're going to ignore the terms in our x column, multiply our first diagonal, 1 times 2, minus multiply the second diagonal, 3 times 3, comma. For our y component, we're going to ignore the y column, multiply that first diagonal, 2 times 2, minus the product of the second diagonal, 3 times 1. We just have to remember for our y component, this is going to be the opposite of that. For our z component, ignore the z column, and then product of our first diagonal, 2 times 3, minus product of our second diagonal, 1 times 1. Now we're just doing a little bit of arithmetic here. 1 times 2 is 2, minus 3 times 3 is 9, so 2 minus 9 gives us negative 7. 2 times 2 is 4, minus 3 times 1 is 3, so 4 minus 3 is 1. Now it's our y component, so we're going to make it the opposite of that, so we actually get negative 1. 2 times 3 is 6. 1 times 1 is 1. 6 minus 1 gives us a z component of 5, and there is our cross product. Now, the second thing we were asked to do is show that that cross product is orthogonal to our original vectors, and you might recall from last time that we know two vectors are orthogonal if their dot product is 0. So we're going to find the dot product of vector A with our cross product and the dot product of vector B with our cross product. And remember, to find our dot product, you multiply your x components, multiply your y components, multiply your z components, and add those numbers together. So 2 times negative 7 plus 1 times negative 1 plus 3 times 5. 2 times negative 7 is negative 14. 1 times negative 1 is negative 1. 3 times 5 is 15. Negative 14 minus 1 plus 15 is 0. So our cross product is orthogonal to vector A. Let's take a look at vector B. So multiply our x components, 1 times negative 7, plus multiplying our y components, 3 times negative 1, plus multiplying our z components, 2 times 5. 1 times negative 7 is negative 7. 3 times negative 1 is negative 3. 2 times 5 is 10. Negative 7 minus 3 plus 10 is also 0. So we have shown that our cross product is orthogonal to our original vectors. For example 2, we're going to find a unit vector that is orthogonal to both vector u, which is equal to 2i plus 3j minus 4k, and vector v, which is equal to negative I plus 2j. So first, to find a vector that's orthogonal to two vectors, we find the cross product. And there, I'm reminding you of our formula again. So if we put in our x, y, and z components, we have 2, 3, and negative 4 for our vector u. We have negative 1, 2, and since there wasn't a k component, 0 for our z component in our vector v. So now if we find our cross product, so for our x component, ignore the x column. Product of the first diagonal, 3 times 0, minus second diagonal, negative 4 times 2. Find our y component. We're going to ignore the second column, the y column. Product of the first diagonal, 2 times 0, minus second diagonal, negative 4 times negative 1, comma. To get our z component, we're going to ignore the z column. Find the determinant. So first diagonal, 2 times 2, minus second diagonal, 3 times negative 1. Well, 3 times 0 is 0. Negative 4 times 2 is negative 8, and 0 minus negative 8 gives us positive 8. 2 times 0 is 0. Negative 4 times negative 1 is positive 4, and 0 minus positive 4 is negative 4. But then again, our y component is the opposite, so we're going to turn that into a positive 4. 2 times 2 is 4. 3 times negative 1 is negative 3. 4 minus negative 3 gives us a positive 7 for our z component. Or using our unit vector notation, our standard unit vector notation, that would be 8i plus 4j plus 7k. So that's our cross product, but the problem didn't ask us for the cross product. It asked us for a unit vector that's orthogonal. So now we need to find a unit vector in the direction of the cross product. And to find our unit vector, we start by finding our magnitude. Remember, our magnitude is the square root of each of our components squared added together. So the square root of 8 squared plus 4 squared plus 7 squared works out to give us the square root of 129. And now, to get a unit vector, you just divide each component of your vector by its magnitude. So our unit vector would be 8 over square root 129, comma 4 over square root 129, comma z over square root 29, or in that standard unit vector notation that IJK form, 8 square root 8 over 1. Ooh, goodness, let's try that again. 8 over the square root of 129i plus 4 over the square root of 129j plus 7 over the square root of 129k. And now you all know that normally I would be asking you to rationalize your denominators, but for some reason in this one section of your book, they don't actually make you rationalize your denominators. So to get the correct answer, you have to leave it in what I would consider an incorrect form. Do note that if you're doing your assignment on WebAssign, make sure that you write your answer using the same notation as the vectors in the original problem. So if the original problem gives you vectors in component form, you would write your answer in component form. If your original problem gives you vectors in the unit vector notation, then make sure you use that notation when you write your answer. Okay? So don't feel like you even have to write both types of notation. Use whatever type of notation the original vectors are given. All right, next up, area formulas for parallelograms and triangles in space. You might recall your formulas for parallelograms and triangles in two-dimensional geometry, right? The area of the parallelogram is equal to the base times the height. The area of the triangle is 1/2 base times height. It looks a little bit different when we're in three-dimensional space. And it turns out that the magnitude of the cross product is equal to the area of the parallelogram that has vectors u and v as adjacent sides. And now recall that triangles is half of a parallelogram, so half the magnitude gives us the area of a triangle that has u and v as adjacent sides. So example 3, we're going to show that the quadrilateral with vertices at point A, 3, 5, 0, B with coordinates of 1, 2, 4, point C with coordinates of 1, 3, 4, and point D with coordinates of 3, 6, 0 is a parallelogram. And then we're going to find its area. Now, I started by drawing a quick sketch of a parallelogram, and I just went around and labeled the corners, the vertices, A, B, C, D, and then added in the coordinates. Now, you may notice that this isn't a terribly accurate diagram because the x-coordinate of 1 should probably have been the points over here and the ones that had an x-coordinate of 3. But we're just not going to worry about that because what we really need the diagram for is to help us figure out the component forms for our vectors. Okay? So the first thing we're going to do is find the component form for the vector for each side of this quadrilateral. So the vector from A to B, the vector from C to D, or D to C, you could do it either way, from A to D and from C to B, or B to C. It doesn't matter which way you have your vectors go. Okay? So from A to B, from 3 to 1 is -2. From 5 to 2 is -3 spaces. From 0 to 4 is 4 spaces for our Z component. You can also use the formulas that we saw in the previous section where you subtract the terminal coordinate minus the initial coordinate. If that's easier for you, you can do it that way. All right, the vector from C to D, from 1 to 3 is -2. From 3 to 6 is -3. From 4 to 0 is +4. All right, the vector from point A to point D, from 3 to 3 is 0. From 5 to 6 is 1 space in the y direction. And from 0 to 0 is no spaces in the z direction. And the last vector we need is from C to B or B to C. I went from C to B. So in the x direction, from 1 to 1 is 0 spaces. From 3 to 2 is 1 space. And from 4 to 4 is 0 spaces. Now, in order for us to know that this is a parallelogram, that means we need 2 pairs of parallel sides. And we know that vectors are parallel if there is a scalar multiple. If there is a number you can multiply one vector by to get the other vector. So notice that if I multiply vector AB by 1, I get vector CD because they happen to be the same. Now, if you had gone from D to C, these components would have been the opposite, but that would have just meant that your multiple would have been -1. And so you would have still known that they were parallel. And then also notice that my vector AD and my vector BC are the same in component form, so I could multiply vector AD by 1 to get vector CB. So I also know that these two vectors are parallel. So since we have 2 sets of parallel sides, 2 sets of parallel vectors, we know that this is a parallelogram. And since it's a parallelogram, we can find its area by finding the magnitude of the cross product. So we need to find the cross product of adjacent sides. Okay, so I used vector AB and vector CB, but you could use any pair of adjacent sides. So you could also use AB with AD, you could use AD with CD, you could use CD with CB. Does not matter which pair of adjacent sides you use, okay? So we find our cross product, same way that we did before. So x component, ignore the x column. First diagonal is -3 times 0 minus second diagonal is 4 times 1. For our y component, we ignore the y column. Our first diagonal then becomes -2 times 0 minus our second diagonal is 4 times 0. Remember, since our y component, this is going to be the opposite of what we get from that mathematics there. And then for our z component, ignore the z column. Our first diagonal becomes -2 times 1 minus our second diagonal, -3 times 0. If you simplify those, we get a cross product of -4, 0, -2. And now we just need to find the magnitude of this cross product to determine the area of our parallelogram. So the square root of -4 squared plus 0 squared plus -2 squared, well, -4 squared is 16, 0 squared is 0, -2 squared is +4. So 16 plus 0 plus 4 gives us the square root of 20. On your calculator, you could simplify that. That's about 4.5. Since we weren't given it any units originally, we would just label this as having an area in square units, in generic square units. Okay. All right. Next up, planes in space. And recall from our last lesson that to determine the equation of a line in space, we used a point on the line and a vector parallel to the line. To determine the equation of a plane in space, we use a point on the plane and a vector normal or perpendicular plane. So notice we've got another word here, normal, which means perpendicular. So normal, perpendicular, orthogonal are used rather interchangeably in your book when we're referring to vectors. If you go on to future math classes, they get more specific uses that apply better to certain situations. But for what we're doing right now, just know that they're being used interchangeably and mean perpendicular when we're referring to vectors. All right, so consider a plane that has the point P with coordinates x sub 1, y sub 1, z sub 1, that has a non-zero normal vector n with components of a, b, and c, as we see in our diagram. Now, because vector n is normal or is perpendicular to this vector here, PQ, okay, then we know the dot product of those two vectors is going to be 0. And that's what's going to allow us to define our equations for the plane in space. So we know that the dot product of vector n with the vector from P to Q, and it doesn't matter where you put that point Q, okay, will be 0. Okay, so vector n has components of a, b, and c. P had coordinates of x sub 1, y sub 1, z sub 1. Q has coordinates of just x, y, and z, so we can find our component form by subtracting our x coordinate, subtracting our y component, subtracting our z components. Okay? So if we find the dot product of these two, we know it's equal to 0. So that leads to our standard form equation of a plane in space. If we were to distribute, right, to find our dot product, you multiply your x components, so a times x minus x sub 1, and plus multiply our y component, so b times y minus y sub 1, plus our z component, c times z minus z sub 1. We know that those all have to add up to equal 0 if these two vectors are normal or perpendicular. To get our general form, your book defines it like this: a times x plus b times y plus c times z plus d is equal to 0, where this expression is equal to d. Please don't worry too much about this expression, because really what we're going to do is write our standard form equation and then transform that into our general form equation. So in example 4, we're going to write the equations, both the standard form and the general form, for the plane with a point -4, 3, 5, and a normal vector n is equal to -2i plus j minus 3k. So our point gives us our x sub 1, our y sub 1, our z sub 1. Our vector gives us our a, b, and c. And since j can be written with a 1 in front of it, we know that's 1 for our b value. So now we can substitute our x1, y1, z1, and our a, b, and c into our standard form equation. Okay, so a is negative 2 times x minus x sub 1 is negative 4, plus b is 1 times y minus y sub 1 is 3, plus c is negative 3 times z minus z sub 1 is 5. Now, if we simplify this a little bit, when I subtract negative 4, that's like adding 4. So we have negative 2 times x plus 4, plus 1 times y minus 3. Instead of writing now we're adding negative 3, we can just write minus 3 times our z minus 5 is equal to 0. There's our standard form equation. To get our general form equation, all we're going to do is distribute each of these sets of parentheses and then combine our like terms. So negative 2 times the quantity x plus 4 gives us negative 2x minus 8. 1 times y minus 3 gives us y minus 3. Negative 3 times the quantity z minus 5 gives us negative 3z plus 15. Make sure you distribute. Negative 3 times negative 5 gives us positive 15. And now if we combine our like terms or constants, negative 8 minus 3 is negative 11, plus 15 is positive 4. So our general form equation is negative 2x plus y minus 3z plus 4 is equal to 0. We have one last example for this video. Example 5, we're going to find the general form equation of the plane passing through the points 3, 2, 2, 1, 5, 0, and 1, negative 3, 1. Whatever point they list first, you're going to use as your initial point, your p, your x sub 1, your y sub 1, your z sub 1. Okay? The first thing we're going to do is find vectors for our initial point to both of these other points. Okay, so just getting it in component form. So I'll call them vectors u and vectors v, although the names isn't super critical. So from 3 to 1 is negative 2, from 2 to 5 is 3 spaces, from 2 to 0 is negative 2 spaces in the z direction. All right, from our initial point here to this point here, from 3 to 1 is negative 2. From 2 to negative 3 would be negative 5 spaces. From 2 to 1 is negative 1 spaces. All right, so at this point, we've got some vectors for our initial point to these points. The reason we want those, and I probably should have said this first, is that in order to write the equation of plane, we need a point and we need the normal vector. We need a vector that's perpendicular to the plane. Well, hey, if I have these two vectors, if I want to find a vector that's perpendicular or orthogonal to both of those, we're going to find the cross product. Hey, another case where the cross product comes up. So finding that normal vector is our cross product. So just like we were doing before, put in your first vector's components, put in your second vector's components. For our x component, we ignore our x column, find our determinant, multiply our first diagonal 3 times negative 1 minus our second diagonal negative 2 times negative 5, comma, for our y component, remember that it's the opposite. Ignore the y column, and then our first diagonal becomes negative 2 times negative 1 minus our second diagonal, negative 2 times negative 2, comma, for our z component, we ignore our z column, so now our first diagonal is negative 2 times negative 5, minus our second diagonal, 3 times negative 2. 3 times negative 1 is negative 3. Negative 2 times negative 5 gives us positive 10. So negative 3 minus 10 is negative 13. Negative 2 times negative 1 is positive 2. Negative 2 times negative 2 is 4. So 2 minus 4 is negative 2. And then when we make it the opposite, we get a positive 2. For our z component, negative 2 times negative 5 is positive 10. 3 times negative 2 is negative 6. So 10 minus negative 6 is positive 16. There's our normal vector. So that's going to be our values for a, b, and c that we can now substitute into our standard form equation along with our x1, y1, z1 from our initial point. So if we do that, A is negative 13 times x minus x sub 1 is 3 plus B is 2 times y minus y sub 1 is 2 plus C was 16 times z minus z sub 1 is 2. There's our standard form equation, but it actually asks us for our general form equation. So now if we distribute that, negative 13 times the quantity x minus 3 gives us negative 13x plus 39. 2 times the quantity y minus 2 gives us 2y minus 4. 16 times the quantity z minus 2 gives us 16z minus 32. And if we combine our like terms, our constants, 39 minus 4 minus 32 gives us a positive 3. So our general form equation is negative 13x plus 2y plus 16z plus 3 is equal to 0. Here is your assignment for this week. Please let me know if I can assist you in any way. This is going to be your last assignment out of WebAssign or the book for the year. So give it your best effort.